We're on to Unit 6, and Unit 6 is Thermodynamics, also called Thermochemistry if you want to look at it. And so we're looking at thermo meaning heat and the dynamics of heat changes in a system and its surrounding. When it comes to heat, we do need to understand temperature, and when it comes to temperature, we do need to understand kinetic energy. So there's a lot of overlap from the previous unit as we go through this unit. Why do we go into thermodynamics? Because thermodynamics tells us whether a reaction will occur or not. Reactions that occur are considered spontaneous reactions, and they actually depend on the enthalpy, which is your heat content, but also depends on entropy, which is something called delta S. It's our disorder. And then also it depends on temperature. So all those variables play a role in whether a reaction will occur or not. Go ahead and read our learning objectives one by one. Always do a read at the first beginning of a unit to get a big idea, to get the big picture of what you're going to be learning. And then read it at the end of a unit again, just to make sure you see if we've gone through each of these bullet points one by one. So the first thing we'll talk about is we're going to introduce thermodynamics with temperature and kinetics. So temperature, as we learned when we were learning gases, is the measurement of average kinetic energy of particles. The higher the temperature, the higher the kinetic energy of those particles. The Kelvin temperature is what we're looking at. It's directly proportional to the average kinetic energy. For example, by doubling the Kelvin temperature, it doubles the average kinetic energy. Now, absolute zero is when we're approaching 0 Kelvin. And particles at absolute zero have no motion, so zero particle motion. We're going to revisit the Maxwell-Boltzmann distribution graph, and it shows how particles at higher temperature have more kinetic energy than those at lower temperature. So looking at this graph, you'll notice that at lower temperature, this is what the graph looks like. But what happens is when you have a higher temperature, this same area underneath this graph at lower temperature is going to be the same constant. And so in order for the particles, more particles to meet the activation energy, you need to broaden this curve a little bit or flatten this curve. And so note once again, this area down this below this lower temperature curve is going to be the same area under here. But the activation energy, wherever it sits, say it sits right here. So this is my E of A. Notice how the area under the curve for the cooler temperature is right here. So that's the number of particles that meet that activation energy and form your products, versus hot, which is this area under this right here. So this is where the number of particles increase because they meet the activation energy because they have more kinetic energy. Particle diagrams with vectors can be illustrated with differing kinetic energies. So this is going to show low temperature right here. And what you're seeing is lower vectors here, smaller vectors. And then higher temperature, you'll see bigger vectors. So this is the particle diagram to help illustrate for our temperature differences. Because it's not dynamic enough for you to see, you're actually seeing it through the vectors. So longer vectors versus shorter vectors, which are these arrows. Heat. Heat is actually when kinetic energy is transferred from one object to another. That flow, so heat is a process. It's a process of energy flowing, and that is what we call heat. It measures the amount of heat. In order for us to measure the amount of heat, it's calculated by using Q equals, I used to call it MCAT. So Q equals MCAT is how we measure heat. And it's going to depend on the mass of the substance. It's going to depend on this heat capacity of the substance as well. In other words, how much does it, how well can that object's material absorb heat before 1 gram of that substance changes by 1 degree Celsius. And then, of course, you're also going to need to know the change in temperature. So this is what the delta is, the difference in temperature, final and initial. Q is always a positive value, so make sure you note that Q is a positive value. There are 3 laws of thermodynamics. The first law is that energy can be converted from one form to another, but can neither be created nor destroyed. Very similar to the law of conservation of mass, this is actually the law of conservation of energy. Second law says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So this will be something you'll see when we get to entropy and discuss entropy. And then the third law involves entropy as well. The entropy of a perfect crystalline substance is zero at absolute zero, which is 0 Kelvin. So none of the particles are moving, so you're not going to see any form of disorder arranged for a solid, a perfectly crystalline solid. All right, there's this little symbol right here. It looks like a degree symbol, and it actually represents a set of conditions. The set of conditions is pressure is 1 atm, temperature is 25 degrees Celsius, and the molarity, if it's a solution, is 1 molar. Of course, you'll oftentimes see it with these 3 different variables, whether it is the change in Gibbs free energy at standard conditions, or the change in enthalpy at standard conditions, and then or the change in entropy at standard conditions. Now, why do we look at changes? We're looking at the difference between the reactants and the products. It's always the changes that occur between the reactants and products in a chemical reaction that we're measuring, whether it is Gibbs free energy, enthalpy, or entropy. Gibbs free energy measures spontaneity. It actually is truly the ultimate variable that we want to calculate to find out whether a reaction will occur and really occur without any continual source of energy. In other words, whether a reaction can do work for us. We'd like to know that a chemical reaction is able to garner more energy out of it than what we put into it in order to do work for us. Whether it's power a car, or launch a rocket ship, or work my calculator, have it working, turn on a TV. We want to make sure all the chemical reaction that is involved is able to do work for us. The other variable we're going to need is enthalpy. Enthalpy is basically heat content. So it's measuring the heat content in a chemical reaction. Notice the units for these two, kilojoules per 1 mole. So we really do need to know how much per 1 mole of a substance, or per 1 mole of a substance in the reaction. Delta S is the change in entropy, so we're measuring disorder, and nature favors disorder. That's why entropy is always increasing in the universe in a spontaneous process. So the entropy of the universe is always increasing, of course, as we mentioned. And so how we discern how a reaction's entropy is increasing or decreasing is we know that 2 moles of anything is going to be greater than 1 mole. So there's more disorder in 2 moles than 1 mole. There's more disorder in gases than liquids than solids. Solids are much more orderly. Gases are very disorderly. So we know this relationship. We also know that pure substances versus solutions. Solutions are mixtures of 2 or more different things. Substances, and so that's why you're seeing there's more disorder in solutions. So let's go ahead and circle all that involves more disorder. So 2 moles is more disorder, gases are more disorder, and solutions are more disorder. Now, I want you to notice the units. The units are very important. So the unit of entropy is in joules per mole times Kelvin. And so you've got to make sure that you want to be consistent when you're using all three of these variables in an equation. So this joules, I tend to take this joule unit, joules per mole times Kelvin, and convert it to kilojoules. I really do, because these two are in kilojoules already. So I like to be very vigilant of this unit to make sure I do that. So when delta G is less than 0, negative, that is, the reaction is spontaneous. Equals 0 means you're at equilibrium. Greater than 0 means the reaction in that direction is non-spontaneous. Likewise, if the reaction or delta H is less than 0, which is negative, it's exothermic. Greater than 0, endothermic, okay? If the S is less than 0, which is negative, there's more disorder, and then greater than 0, meaning less disorder. And I really do like to think of entropy as just this word, disorder, more or less disorder. The equation that you're going to see that involves all three of these variables is this comprehensive equation. Again, always noticing your units to make sure they're consistent when you're calculating. Let's go into ionic compounds and ionic bonding in ionic compounds. How do I know the formation of an ionic compound is a thermodynamically favorable process? Well, we approximate that process through something called the Born-Haber cycle. Now, this is not on the AP exam, but it's good for us to understand it for the idea that most of these processes, formation of anything or any kind of reaction, oftentimes involves multiple processes. So we're going to go through this so we can trace the energy involved in the formation of lithium fluoride from its elements, which is lithium and fluorine gas, F2 specifically. So the first part of this formation of this ionic compound is we first have to take this solid metal, lithium, and turn it into a gas. And that is a sublimation process, and that is endothermic. And you can tell it's endothermic because you see a positive delta H. Remember, delta H positive is endothermic. Continuing on with the Born-Haber cycle. You then check to see, you also have to take your diatomic molecule, and I'm going to put these arrows in. And then you have to split them up into singular gaseous atom. So this is what you're seeing here, and this is called bond energy because you've broken the FF bond. And in breaking that FF bond and halving that this is how you get fluorine here. So this is an endothermic process. Once again, positive delta H is an endothermic process. And we call this bond energy. Then we have to take that gaseous lithium atom that we made earlier when we sublimated metallic solid lithium into gaseous lithium. We have to ionize it. And we're going to remove an electron. Upon removing an electron, we now have lithium ion, which is what we want to make our ionic compound. And so this is called ionization energy. And once again, that's an endothermic process. Right here in this step, we're going to ionize fluorine gas here, but we're going to add an electron to that. Instead of removing an electron, we're adding an electron, which means it's electron affinity. And so this value is the value for how much energy we need to that will be released as a result of adding an electron. And that is an exothermic process. Delta H is negative. Here we then combine the two ions that we formed and we make our ionic compound, which is our solid lithium fluoride. Our two gaseous ions make our solid lithium fluoride, and that is an exothermic process. And this is called lattice energy. Now you add them all together, all this whole equation, you get this final equation overall. And you also add their delta H's for each of these steps. And this tells you that this reaction is very exothermic. And exothermic reactions are often favorable reactions. Not always, but often favorable. So the formation of an ionic compound is favorable because of this negative delta H exothermic reaction. This shows you the energetics of this, the enthalpy of this, as we're going through these steps right here. Pretty much lining it up and showing you that overall, in the end, given all that is required, so all the up arrows plus the down arrows, you're going to have more down, in other words, energy release, than energy absorbed. So up arrows are energy absorbed, down arrows are energy released. Okay, well, let's first talk about the standard change in enthalpy. So we're looking at heat content overall. And heat content is really heat stored in bonds. And so we're looking at what is called potential energy changes. So enthalpy is really measuring potential energy changes in a chemical reaction. And so with that, we calculate what is called bond dissociation energy because, again, potential energy is stored in the bonds. And that energy is calculated using bond dissociation energy, the energy required to break a covalent bond in 1 mole of gaseous molecules. Heat energy, which is Q, is the amount of energy absorbed, which we said earlier was a positive Q, versus release, which is a negative Q. Q itself is never positive or never negative. It's always a positive value. But we add the word, based on these words right here, we add the appropriate sign to account for the fact that Q could never be a negative value. So with enthalpy, changes in enthalpy, you're going to come across 3 different kind of subscripts: F, RXN, and COMB. They stand for, this is the change in enthalpy of formation. F stands for formation. This is a change in enthalpy for a whole reaction. And then, of course, this is the change in enthalpy for a specific reaction called a combustion reaction. So we're going to learn to distinguish one from the other using a chart later on. But let's talk about formation. Standard change in enthalpy of formation, which is delta H standard F. Okay, it's the heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atm. For a substance in its free elemental state, the delta H of formation is always 0. So let's talk about that. You're going to need to refer to this lovely reference sheet. So you'll need this link here for you to be able to access this information for the delta H values. Okay, so according to this appendix, I found out that the heat of formation of 1 mole of CH4, notice there's only one of them, 1 mole of it, from the elements, which is carbon, solid, and hydrogen gas. Those are the elements that make up CH4. Now notice how the formation of oxygen from oxygen, there's no change that you're seeing in the substance itself. So that's why the heat of formation of an element in its free elemental form is 0, as you see here. I wanted to prove to you that it's 0 based on what you're seeing here. No changes. Now you see carbon dioxide, 1 mole of it, and of course the 2 substances that make up carbon dioxide are carbon and oxygen. And so that's what you're seeing here in the heat of formation of carbon dioxide. Now these are all values that you obtain from this appendix or given to you in a problem. Now let's look at water. I wanted to show water because water, 1 mole of water, is made up of half a mole of oxygen. Half of this will give you 1 mole of oxygen. So that's why you're always looking at 1 mole being formed of your substance from their elemental makeup. And so you will see fractions or other whole numbers in order to try to account for the equivalence or the balancing of this reaction. Again, these values are obtained from the appendix. Now we get to standard change in enthalpy of combustion. So it's combustion reaction. It's the overall heat change from the reaction of 1 mole of a substance with oxygen. So whatever your combustible material is, it's 1 mole of that combustible material. So if you look at this reaction, it's a combustion reaction. So who's your combustible material other than oxygen? So here's oxygen. The combustible material is CH4, and there's only 1 mole of it, notice. And so this is the heat of combustion. And so it's the ending, it says kilojoules per mole of this reaction. It really is 1 mole of per 1 mole of the CH4. Also, it also means per one, since there's a 1 coefficient here also, that means it's 1 mole of carbon dioxide. So this is the amount of energy that's released. Notice the negative means release from per 1 mole of carbon dioxide that forms. So take a look at this. It's really important for you to understand how to interpret this value, especially the per mole here that you're seeing. So for 1 mole of CH4 that combusts, you're producing 890.4 kilojoules. For 1 mole of oxygen, but since this represents this amount of energy is for 2 moles, for 1 mole is half of that, which is 445.2 kilojoules. And then carbon dioxide, since it's a coefficient of 1, so that means this is the amount of energy. So 1 mole of carbon dioxide produces 890.4 kilojoules, just like methane. Notice how they're both the same coefficient. And I'm going to write that in just so you can see those the same coefficient, okay? And then underline the 2. Now we get to water. Notice water, this is representing how much energy is released for this whole reaction, but this reaction involves 2 moles of water. So that means half of that is how much is going to be produced for 1 mole of water. So understand this per mole of reaction represents all, or for this whole reaction, 1 mole of each of these two because it's 1, but then half that amount is per 1 mole of each of these, okay? How much heat is generated for the combustion of 100 grams of methane? So the first thing I want to do is, here's my methane. I want to convert it to moles. So I'm going to do a gram to mole conversion using dimensional analysis. And then I know that every 1 mole of methane, that 1 mole of methane produces 890.4 kilojoules. So I do my dimensional analysis, calculate it all, and don't forget to always make sure you're cross-canceling your units that you're supposed to cross-cancel and end up with the unit that you want and desire, which is kilojoules, the amount of heat. The same thing goes for the next problem, but now you're dealing with oxygen. So 100 grams of oxygen converted to moles. And then we know that every 1 mole of oxygen produces 45.2 kilojoules. Now you could have put 2 moles here and then put that 890.4, but you'll notice the ratio is going to reduce down to 445.2 per 1 mole of oxygen. Once again, always making sure you cross-cancel your units as you see appropriate, and that is how you calculate the amount of heat produced by a certain amount of your reactants or products. All right, let's go to standard heat in enthalpy, or in enthalpy of a reaction. So now we're dealing with delta H of a reaction. It's the overall heat change from any chemical reaction. So it actually, this encompasses this as well as this. So it can actually be any of these types of reactions, whether it's a phase change, fusion, so melting, vaporization, so liquid to gas, Ions, which means you're ionizing a substance. Solution, so you're reacting to solutions to make a driving force of some sort. And then you have your heat of combustion, which is C2H2 reacting with 3 moles of oxygen to form water vapor and 2 moles of carbon dioxide. So this is a heat of combustion reaction. And then there's heat of formation, where you're forming 1 mole of a substance from the elements that make up that substance, okay? You can figure out from the positive or negative of these delta H values, whether it's the heat of fusion, vaporization, ionization, or combustion formation. You can tell whether it's endo or exo. Once again, positive, endo, negative, exo. All right. So it's really important that we learn how to distinguish one or the other. Oftentimes, every single reaction is, whether it's formation or combustion, is a heat of reaction. So all of these they're all heat of reaction because they're any type of reaction where you're forming a new substance is a heat of reaction, okay? Now, combustion is always 1 mole of a combustible material with oxygen. So if you're seeing 1 mole of that combustible material reacting with oxygen, so this is heat combustion. So I keep on going. This is also heat combustion because it's reacting with oxygen. Here's your combustible material. I know you've always learned that it's a hydrocarbon, but any oxygen, any substance reacting specifically with oxygen to form metal or non-metal oxide is your heat of combustion, or it's a combustion reaction. This is not a heat of combustion reaction. It is actually a heat of formation because you're forming 1 mole of that substance. So notice there's a 1 here, invisible, but you're forming it from the elements that make up that 1 mole. So very different. Notice how they look very different, or they're a little different. One is 1 mole of the product versus 1 mole of the combustible material. So that's what makes this a heat of formation. Now you get to this is also combustion because you're seeing that your 1 mole of your combustible material forming your oxides of your substances, whether it's your nitrogen oxide or a hydrogen oxide of some sort. As you keep on going through, you'll notice that this one right here is forming 1 mole of your substance. So from the elements, which is carbon and hydrogen, notice this substance has both carbon and hydrogen. So from the elemental substance, 1 mole of it, you're forming, so this is a heat of formation. This last one is a 1 mole of the substance from the element, so it's a heat of formation, but it also is a heat of combustion as well because you're combusting only 1 mole here with oxygen to form your product. So this one has all 3. A little tricky. So very important for you to know what is a heat of formation versus heat of reaction, which they're all, but also heat of combustion. So really you're distinguishing heat of formation and heat of combustion. There are 3 ways or 4 ways to calculate the delta H of a reaction. You can use bond energy, which is really what you learned last year. You're just summing up the bond energy of the reactants minus the bond energy of the products. Now, breaking, understand that when you're breaking, AP doesn't give you this equation, but you have to understand this equation. So when you're breaking bonds, it's an endothermic process, and that's why you're seeing a positive right here. Whereas when you're making products, which means you're making bonds, this is an exothermic process. You're making bonds, your heat is released. And so notice how there's a negative here. So exothermic, negative, endothermic, positive. So with this equation, you're actually seeing the enthalpy work out between the reactants and products. You'll need average bond energy, and I'll show you what that looks like. It's a table of bond energy. You've seen it last year when you were doing thermo. Now, had we had our time last year, we would have been able to calculate also using Hess's law, which is the heat of formation, using heat of formation values given to us, forming 1 mole of the formation of 1 mole of each of the products and the reactants, and then we sum it and subtract it. There's also Hess's law, the indirect method, which is the summation of the elementary steps. So this is a very, I find it's very much like a problem-solving approach to finding the delta H of a reaction. And then the third way, which is what you learned last year, so you actually learned bond energy and heat, calculating heat of formation through this equation, Q equals or delta H of a reaction equals Q divided by M, which is mass, or molar heat of a reaction, which is over N, which is moles. So heat Q over N. And there are varying units here that you're going to see for Q, which is joules or kilojoules, and then mass is grams, N is moles. We're going to actually see all 4 ways calculate for the same reaction, and we're going to see how the values are consistently pretty much close enough between one method of calculating versus another. So the first one is average bond energy. And so this is the equation. You're taking the bond energy of the reactants minus the bond energy of the products. I like to really abbreviate it. And then just a reminder, breaking bonds is endothermic. So that's why there's the BE is positive, whereas forming bonds releases energy, and that's exothermic. That's why the BE is negative, the bond energy. Let's go ahead and look at the table of average bond energies. This is the table, and in this table, which is given to you, there's basically the amount of energy to break certain bonds. And of course, the amount of energy to break multiple bonds versus single bonds versus multiple bonds would be higher than multiple bonds would be higher than single bonds. So take a look at this and kind of study it and go and be able to understand some of the trends that you see. You know, why is NF got a higher bond energy than NH? Sorry. NO. I shouldn't use NH. NO. So why is NF higher than NO? Well, you can look at electronegativity and the attractive forces that bond these two atoms that would bring them closer or farther away. And F is very electronegative, we know. So you can study it and kind of look at some of the trends, of course, based on your periodic trends. What we're going to do is we're going to calculate the enthalpy using bond energy, this chart right here. And the first thing you want to do when it comes to using bond energy is to draw the Lewis structures of all the bonds that are in that structure. So if I draw CH4, this is what the Lewis structure looks like. 2 O2s. O2 is bonded through a double bond, and there's 2 of them. So I note that I draw 2 of them. And then, of course, CO2 here, and then 2 water molecules. So I draw all of them so I know what I'm breaking and how many bonds I'm breaking of each, okay? So the first thing I want to do is I look up CH bonds, and I see it's 413. And there's 4 of them. 1, 2, 3, 4. So I times that by 4. 413 times 4. That's my one of my reactant. Now I go over to the other reactant, which is O2, and I'm looking for a double bond. So 495, and there's 2 of them. There's 2 of them. 2 double bonds, so I double that. So then I multiply and then add these 2 reactants, the bond energy of the reactants. And then I would then subtract it from the products. So what's in my products? I see 2 CO bonds. So I go to my CO double bonds, that is. So 799 times 2. There's 2 of them. 1, 2. there's 4 OH bonds. This is why I have to draw all the Lewis structures out. There's 4 of them. So I go and find 4 OH bonds, 463, and I multiply by times 4. I add them together and then I subtract. This is my delta H of this combustion reaction here. So I found that this specific combustion reaction releases, that negative means it's exothermic, releases 808 kilojoules per 1 mole of the whole reaction. Really 1 mole of the methane or 1 mole of the carbon dioxide. Now I go to the next method. The next method is the Hess's law, the direct way, using heat of formation values, which means I'm going to have to look up these values. And when I do look up these values, this is what I've obtained from this chart here, this reference sheet, this appendix. I see all my values for each of my substances. I'm looking up really my reactants and my products. And I find out and just report it right here, all my reactants and products. I do want to note the states of matter because states of matter are going to change the heat or the amount of energy that is potential energy inside those substances. So I do want to make sure I'm looking, when I look it up, I'm looking for the correct states of matter as well. With the enthalpies, or the heat of formation values that I looked up in the reference sheet or appendix, I report it right here, and it is per 1 mole of each of these substances, so I do have to consider the stoich as I go through my calculations. So I begin with my equation. So sum of the heat of formation of the products. The products are these 2 substances, carbon dioxide. There's only 1 mole of carbon dioxide, and there's 2 moles of water vapor, so I'm going to put 2 moles, right, twice that, twice the negative 242 kilojoules per 1 mole of it. So add up your the heat of formation of the products minus, and I would do the same thing for the reactants. There's 1 mole of the methane, 1 mole, and then oxygen is not is 0 because the heat of formation of an element is 0 from the elements that make up this element is 0. So that's why this is reported as 0. I times it by 2 still, but notice it's just to understand that there's still stoichiometry, but it's 0. So I calculate my value and I see that the heat of this reaction based on the heat of formation values is negative 802.5 kilojoules per mole. Not far off from the bond energy, using bond energy to calculate. Now we use Hess's law indirect method, and this is just basically we're manipulating different elementary steps to figure out the final reaction, and the same final reaction is what I'm looking for, the heat of combustion of this reaction. So the first thing I want to do is here are all the different chemical reactions that are given to me. Some of them are combustion, vaporization, and formation, so it's a combination of different types of reactions. And what I'm going to have to do is I'm going to have to manipulate this to get these reactions to get my final reaction. And upon manipulating these reactions, I will then account to do what I need to do with the enthalpy of their values for those reactions. So the first thing I want to do is find my least frequent elements. CH4 is my least frequent elements, so I find CH4. And they're all least frequent, but it's easier to deal with a unique substance like CH4. And I only see it once right here. And I see it in the reactant. In the product in this reaction that's given to me with its enthalpy. So I need to flip this reaction. I know I'm going to have to take this reaction and flip it so I can have CH4 in the reactant side. In doing so, in flipping that reaction, I'm actually going to change the sign because now my products have become reactants and my reactants have become products. So I'm going to change the sign, which is put the negative of that. Now, so I'm done with CH4, accounting for CH4. Notice I flipped that reaction. Now I go over and find something else that's unique. And I'm looking to see, comparing these reactions to these substances. And I see CO4, or carbon dioxide, is pretty unique. And it is positioned in the products like it is in the original equation that I'm trying to find the enthalpy for. And so I am happy to keep this as original. So this reaction is going to be kept as original, so their value stays as original, as originally stated. The next one, water. Now this is water liquid versus water vapor. And I want water vapor, so I need to double this reaction. Why? Because there's twice the water vapor, so I'm going to double this reaction. In doubling this reaction, the heat of vaporization, I'm going to double the enthalpy as well, because it's per 1 mole of this reaction, and if you double it, then that means it's twice. The heat is going to be twice produced, twice that amount. But then I need to also get rid of, the, I don't have water vapor in this final reaction. So I need to get rid of the water vapor. And since this has been doubled, this equation has been doubled, I need to double this so that I can cross cancel, like that intermediate when we're doing reaction mechanism, very similar to that idea. So I'm going to double this reaction right here. And as a result, I'm going to see the enthalpy doubled as well. So if you think about everything you've done, you've doubled this reaction, you doubled this reaction, you kept this reaction as original, and then you flipped this reaction. As a result of flipping, you'll notice that the value becomes a negative of that value. And let's add up these reactions. So upon adding these 4 reactions up and cross-canceling what you can see cross-canceled, so there's a 2 right here. I'm going to remember that. There's a 2 right here. Carbon gets cross-canceled. And this is really 1. So I'm going to cross this out and say there's 1, because 2 times 1/2 is 1. So you're seeing the 2 get multiplied into each of these substances, okay? So please don't forget that you're doing that. Now, adding all these up, you should get 1 methane, and you see it right here. You should get 2 oxygens, 2 moles of oxygen right here. 1 mole of carbon dioxide and 2 moles of water vapor. So you're getting pretty much this whole reaction that you were set out to find the heat of combustion for. And so adding all that together, we're also going to add these values also together as well. And in doing so, you get negative 802.5 kilojoules per mole. Now, recall from the previous 2 numbers, from the previous 2 approaches, the bond energy as well as the heat of formation, your value isn't far off from those other values for the same reaction. Let's do the third technique. The third technique is using Q and Q divided by moles, or Q divided by mass. And so you're finding the heat of reaction through either or. I am going to do it by moles. So this is the equation I'm going to use. That's because I was already calculating kilojoules per mole. So I want it per mole. So what is the heat of reaction in kilojoules per mole when 4 grams of CH4 combust, releasing this amount of heat? So here's my Q. And then here's my moles. And literally that is my moles when I calculate it, of course. So I'm going to take my 4 grams of CH4 and convert it to moles. So I have my moles of CH4. And all I'm going to do is take my energy in kilojoules. So here's converted, my joules converted into kilojoules. And I know it's heat release. The word release suggests that my enthalpy is going to be less than 0. And so I'm going to put a negative in front of my Q for that reason. And that's exactly what I've done. And so yeah, you've got your Q value divided by your moles, and notice, not far off. So all four techniques give you similar values for the heat combustion of methane, showing you that you will be using any of the four methods depending what you're given. If you're given bond energy, you're going to use the bond energy equation. If you're given heat of formation values, you'll use heat of formation, which is enthalpy of products minus reactants. And then if you're given a series of reactions like you are here, you're going to just manipulate those reactions to try to get to the final reaction that you want, and thus manipulating the enthalpy for those reactions. And then, of course, the last method, which is using Q. This is one of the simplest method. You take Q divided by moles, and that will be your enthalpy of your reaction. Let's look at how enthalpy plays out in what is called a potential energy diagram. So once you calculate your enthalpy, or we can see enthalpy in this diagram because here's your reactants, here's your products. When we take the difference between the products and the reactants, you'll see the enthalpy. So this is the difference between the products and reactants right here, and that is your change in enthalpy for that reaction. This the y-axis is really oftentimes potential energy, so I'm going to add that into it. And of course, the x-axis is the reaction progress, or you can say time if you want to look at it. This is where the products has lower potential energy than the reactants, which means heat is going to be released out from the system to the surrounding. Here we're going to see what an endothermic reaction. By the way, this is your E of A right here, activation energy, if you can recall. So this is E of A. It's always the hill to climb. And every reaction requires a little bit of energy to start it up, but once you start it up, it gets rolling through. And so in this case, even if you need a little bit of energy to start, you form, there's more energy release than what you need. So what would a reaction that is endothermic look like? Well, an endothermic reaction is going to look like this. I'm going to start low. And oftentimes endothermic has a high activation energy, leading to the formation of your products. So here's your reactants. Here's your products. And true to what we've been consistently saying, activation energy is that hill to climb. And your enthalpy is going to be the difference between the reactants and products. So here's the products up here, and the reactants is down low. So when you calculate your change in enthalpy for this reaction, you'll see that it's going to be a positive value because the products has higher potential energy than the reactants, whereas this one's negative. In example 7, that's precisely what you will be practicing, drawing an energy diagram, labeling the x and y axes, the reactants and products, and they're specific given this reaction right here. You did find out what the enthalpy is, so you should know whether this reaction is endothermic or exothermic based on what you had calculated prior. So it's still the combustion of methane, forming carbon dioxide and water. Pause the video and hopefully you can check your answers after you unpause, but practice first. So if you unpause now, you should see the answer. I put my reactants in, my products in. I made a plausible activated complex. Activated complex is a transition between the two. Hopefully you can see how this becomes the transition between the reactants and products. Activation energy is that hill to climb. And then, of course, enthalpy is the difference between the enthalpy, or the potential energy between the products and reactants, which was negative about 808, negative 808 kilojoules per mole. Make sure you know what the labeling of the x and y axis is. And check your answers. Now we go and jump into standard change in entropy, which is delta S. There's only one way to calculate delta, actually two ways to calculate delta S, but this is the primary way that you'll calculate it from the root from raw data. And so it measures disorder, randomness in a system, and we know that the second law and the third law of thermodynamics involves entropy, and how entropy is always increasing, or if you have 0 Kelvin, the entropy is 0, basically, for a solid crystalline structure. When you've gotten raw data being the entropy of formation values for both products and reactants, so you can sum each part and then just take the difference. If you're asked to predict entropy, the entropy of a gas is more than the entropy of a solid. There's more randomness or disorder with a gas than the solid. The entropy of the solution, which is a mixture of two or more substances, is definitely going to have more disorder than pure substances. And if you add more particles, 2 moles versus 1 mole, there's more entropy. So this is general rules that you want to follow when it comes to predicting. This is upon predictions only that you will see these rules. So if it's asking you to predict if delta S is going to be positive or negative in the end. Positive meaning more disorder, and then if you have a delta H that's negative, there's less disorder. Again, I like to just focus on the word disorder and say there's more or less disorder. Example 8 is, just as we said, was predicting the sign of the change in standard change in enthalpy, or entropy, sorry, for each of the following changes. So it's really conceptualizing what you're seeing and whether you're seeing disorder increase or decrease. I like reminding myself what S positive versus S negative means. If S is more than 0, in other words, positive, that means it's more disorder. If S is less than 0, negative, there's less disorder. Now, remember, S is products minus reactants. So if the change in S, the products has more disorder than the reactants, that means the entropy has gone up. So that's why it's positive. And then, of course, if the products has less disorder than the reactants, that means the delta S is going to be negative, thus less disorder. So looking at the first example, you see 3 moles of gases, 2 moles of hydrogen, 1 mole of oxygen, forming 2 moles of water vapor. I'm assuming this is going to be a gas. It looks like 3 moles becomes 2 moles of gases leads to less disorder, so your delta S is going to be negative in the end. In B, I see liquid becoming liquid water turning into ice. So you're going from a liquid, which is a more disorderly state, to a more less disorderly state, which is a solid. So that means your delta S is going to be negative once again, because there's less disorder here than here. There's more. So when you subtract, you're going to get a negative value. Now we get to combustion. It looks like fire, burning wood here. So it's a combustion reaction. And in burning wood, you're going from a solid, which has a very less disorder, becoming more disorder here with gases. So this is going to form some gases. So solid becomes gases, which means you're going to see the entropy increase, which is a positive value. So delta S is going to be a positive value in C here. Okay, I'd like you to try out the rest of these problems and check your answers, but make sure you give a good justification for each of your answer. Let's jump over to 9 after you've unpaused the video. Predict the sign. Once again, it's more prediction, and so this is more really true to what the chemistry is, where you're actually looking at a chemical reaction and predicting the sign. Here you have 3 moles of water gases, 2 moles of hydrogen, and a mole of oxygen forming liquid. So it looks like the entropy has gone down. So your entropy is going to be a negative value. Oh, it looks like you also have to justify your answer quantitatively, which means you're going to have to use your delta 8 or your appendix and justify it using the appendix, the TRO appendix. I'll do that after we go through each of the predictions. Now we go to the next one. In the next one, we see a solid becoming gases. So it looks like the entropy is going to increase. So it's positive. And then the last one, you see 2 moles of gases becomes 1 mole of gas. So that's a decrease in entropy. It's becoming less disorderly. And so we're going to justify all of this by the calculations. We're going to have to look it up using the TRO reference. I'll go ahead and put a link to the TRO reference in the back here somewhere, on your notes. But I'm going to have to pause the video and look up these values. Okay, so I looked up all those values using the link that I would provide you. So make sure you click on that link and look up each substance. Take note of, again, the states of matter. Always check to see if it's water vapor versus liquid water. These are the values that I got for each of these substances. I am going to have to multiply by the stoichiometry because this value represents per 1 mole of hydrogen, not 2 moles. So I'm going to need to account for that. The equation I'm using is just the entropy, standard entropy formation of products minus reactants. So I'm going to quantify this by summing up the products minus the reactants. And the product really is, there's only it's 70 times 2 because there's 2 moles of the product. Okay? And then minus the sum of the reactants. And there's 2 moles of hydrogen, so I'm going to multiply by that 2, and then add the entropy of formation of oxygen. Now, careful, all substances have some entropy, unless it's a solid at 0 Kelvin. But we're not at 0 Kelvin, we're at 25 degrees Celsius. And so all substances will have some level of entropy. So add up all these and subtract them. I got 140 minus, and I don't have that number quite at hand, but I'm going to do it on my calculator. 467, and subtract those two, I should get a negative entropy. And I do. I get negative 327 joules per mole times Kelvin. So this is the unit for entropy. I'm always going to note that, okay? Yeah, go ahead and work through the next 2 calculations and see if you can justify it quantitatively aside from justifying it qualitatively. Now we get into standard Gibbs free energy. And this is the ultimate variable we are looking for so we can understand whether a reaction will be spontaneous or not. It measures the spontaneity of a reaction or whether it's thermodynamically, my misspelling is right here, favorable or not, okay? So thermodynamic, I shall change that. Favorability. So the equation for to calculate Gibbs free energy, there's several ways actually. You can calculate it once you get your enthalpy and entropy, and then you find out what your whatever temperature it is at, usually 25 degrees Celsius, which converted to Kelvin, so you have to add it to 273 to get your Kelvin units. Good to pay attention to the units because notice how, recall that entropy is in joules per mole times Kelvin. That's why we know that temperature should be in Kelvin in this instance. So noticing the units is very important. So this is the equation that involves all three variables, including temperature. But if you're given the Gibbs formation values, this is the equation you'll be using. So this is the same equation for entropy of formations as well as enthalpy of formation as well. Now, if you're given equilibrium and you're given, R is a constant and temperature is whatever your Kelvin temperature is and your equilibrium constant, you can then calculate delta G also through this route. This is just a rearrangement of the same equation. Your equation sheet on your formula or on your AP constants and equation sheet is given to you in this format right here on the left side. So this is the format that's given to you, but just know that you can rearrange it and you'd get this equation. Now, there's a couple of errors here. This is the equilibrium constant. Should be changed on yours. So this is the equilibrium constant. And I made this, you know how to convert your grams or your Celsius to Kelvin, but this is your Kelvin temperature. So just reminding you that that's a Kelvin temperature. Delta G is going to be in joules. Why? Because if you look at this constant, it's in joules. Delta G is going to be in joules per mole of a reaction. So you're noticing all the units for your constants to help you to know what your ultimate unit for your values are. So this is when you're at equilibrium. Now, when you're not at equilibrium, you're going to utilize the delta G standard, and then you're going to have to deal with Q again. Q again is your non-equilibrium constant. And so you're going to plug it into this equation using your Q constant. And you are given this equation in the voltage form, which is your E volt. And you're going to actually, we're going to cover this when we get to Unit 9, which is our last unit for this year. If K equilibrium is greater than 1, if this K value at equilibrium is greater than 1, you're going to see a delta G value that is negative, which means G value negative means the reaction is not spontaneous in that direction. So once again, I'm going to use my gauge if G is less than 0 versus G is greater than 0. This is non-spontaneous in that direction, in the direction that you're calculating this. So this is when it's negative. And then this, positive. This is spontaneous, which means your delta G is going to be a negative value. And so it's spontaneous in the forward, whatever direction you calculate your delta G, depending if where your products are versus your reactants. So if your KEQ is positive or greater than 1, you're going to end up with an ln that is positive in value. And so when you multiply by negative RT, you're going to get a negative delta G. Now, if it's equal to 0 or equal to 1, ln of 1 is actually 0. So your delta G is going to be 0, which means you're at equilibrium during this time. or your equilibrium is established where the products and reactants are equally favored. So it doesn't. You're still at equilibrium whether it's or K is greater than 1 or less than 1, but this is when neither products or reactants are favored, and so your delta G is 0. When your KQ is less than 1, anytime you have a number that is less than 1 for your KQ, when you take the ln of that, you're going to get a negative value. This negative value is countered by this negative value, which means your delta G ends up being a positive value. Positive value for us means it's non-spontaneous in the forward direction, and of course spontaneous in the reverse. So please be aware, in whatever direction you're noting the delta G to be, and its calculated value to be, is the opposite is true in the reverse direction. And we know at this point the reactants are favored over their products at equilibrium. All right. We have a chart that gives us our G formation values if you need the G formation values. Now, of all elements in their most stable form, the G formation of the enthalpy as well as the Gibbs free energy of all elements is 0, okay? So all substances have entropy, but the enthalpy and the Gibbs free energy of free elements is 0 because there's no change. You won't see any change occurring between the potential energy nor the spontaneity. If you have, so what we're doing is we're going to predict signs and use those signs to predict what G value will be depending on high or low temperature. And when I do this, I'm actually going to I'm going to plug these signs in to each of these variables so I can see it, how it works. So let me show you the first one, how I would do this. So the first one, I would do delta G equals, and then of course a negative value is my H minus T times a positive value for my S. And that's exactly what I've just plugged in as my H value as well as my S value into this equation with the T, which is the temperature. So just looking at these, when I subtract, take a negative minus a positive, which really is a negative value. So I'm adding two negatives together. You could never get anything more than a negative again, whether it's low or high temperature. So my answer to this is it's negative here and negative here, whether it's high or low. I really do like to see my negatives as a positive value, so I put positive with a minus sign in front. So I'm adding two negative values together, and that will always give me a negative value. So in the next one, I would do the same kind of setup, where I'm looking at delta G. If H is positive, so it's endothermic, minus T times a negative S. So I, again, like to look at it in terms of that negative being a positive, and then I'm going to put this a positive because I have to turn it into that. And so either way, whether it's high or low temperature, I know my delta G can only be positive in the end. So then I go to the next, same setup. This is conceptualizing what my delta G has to be prediction-wise. So this is positive, it's endothermic, minus T times another positive. So once again, I like to turn this into a positive value so that I can see that depending on what each of these terms offer us value-wise, magnitude-wise, you might have a positive or negative. In other words, if this term is greater in magnitude than this term, you're going to see a positive value. If this term is greater in magnitude than this term, then it's going to be a negative value. So this is going to be dependent on temperature in this case. So if the temperature is low, so very low temp, this term is going to be very low, which means it's going to most likely be a positive delta G. If this term is high, T is high, that means this term is going to be a high negative value, which means G is going to be a negative value in the end. Okay? So it's dependent on temperature. It really is going to be temperature dependent. So the next one, I'm going to do the same, minus T times minus. And once again, I like to look at it in terms of that subtraction is an addition. So I see that really it's going to depend on which term is going to be larger once again, whether this term for H versus T times delta S is going to be larger. It will dictate whether G is going to be positive or negative. If this is bigger than this in magnitude, you're going to see a negative value for delta H. This is bigger than this, then you're going to see a positive delta G. So this is going to depend on temperature once again as well. But if I specifically say that there's low temperature, so it's low, this value, this term is going to be a low term, which means this negative is going to dominate over the positive, which means it's going to be a negative value. If this is T is high, that means it's going to be positive. So I can do predictions based on what I know of the signs, just purely by the signs of H of a reaction versus the enthalpy of a reaction and the entropy of a reaction. So I can predict what Gibbs free energy is. And that's precisely what I'm going to do first. I'm going to predict the sign of Gibbs free energy from the reaction, and then I'm going to justify my answer by calculating using Gibbs free energy. So in the first one, I'm going to predict the sign, and how I'm going to do that is I know from prior that my delta S, the sign for delta S is going to be, let's see, 3 moles of gas becomes 2 moles of gas, so it's less disorder, so it's going to be a negative delta S. And then delta H is, since this is a synthesis reaction, oftentimes your delta H is going to be exothermic versus a decomposition reaction. So just by prediction, if I have a negative delta H minus a T times negative S, which is a positive. So this is going to depend on the temperature. And that dependency, since we're at 25 degrees Celsius, which is considered low temperature, we know that your G is probably most likely going to be a negative value. And then, of course, we can calculate the G using your actual values. You're probably going to need to calculate the delta H of the reaction, and then you can do your full calculation from that. You can also use geoformations as well, so up to you as far as what you want to do. From the previous, so looking up the appendix, I found out that it was quite easy because these two are elements, and so their H of formation values are 0. So I'm only left with the H of formation of water vapor, and I'm going to multiply by 2 because it is, there's 2 moles of that. And so when I do products minus reactants, I get negative 560 or 572, right? Just double checking. Yes, negative 572. And so when I calculate delta G through this, it's as simple as just making sure you're consistent with your new units, which I was. I converted my joules, or this was from an earlier problem because it's the same reaction. This is the entropy, the change in entropy from the previous problem, and I converted it to joules or kilojoules because this was in joules. And so all my units are consistent. My temperature is 275 or 278 because of 25 degrees Celsius. When I calculate my delta G, it ends up being a final value of, and I'm going to have to work my calculator for this. Negative 474 kilojoules per mole. And that's exactly what we predicted. We predicted a negative value. So you'll go through these steps. You can also use geoformation values. So you actually can also, if you want to go directly through geoformation to get your G of reaction, you're more than welcome to do so as well. I just use the connection because I have the delta S from the previous example number 9, I believe. So I have all those values already calculated. I'd like you to finish the rest and check your answers at the end of this example set. Let's go ahead and do a full-on problem. So starting off with the beginning, reading the beginning, you've got nitrogen monoxide, NO, and carbon monoxide, CO, are air pollutants generated by automobiles. It has been proposed that under suitable conditions, these two gases could react to form nitrogen and carbon dioxide gases, which are components of unpolluted air. Write a balanced equation for the reaction described above. Indicate whether the carbon in carbon monoxide is oxidized or whether it's reduced in the reaction. I'm going to leave that second question as I'm going to teach ahead of Unit 9, which is on redox, and that's oxidation and reduction. So I'm going to give you a little glimpse of it. You wouldn't know how to answer the second question, but I will show you how to answer it. So you're doing this step by step. I'm going to afterwards write the equilibrium expression, which is the Kp for the reaction. Makes sense because they're all gases. I would see a Kp expression rather than a Kc, which is concentration in molarities. But let's do A first. Walking step by step through it. A, I've got nitrogen monoxide gas reacting with carbon monoxide gas, forming nitrogen gas plus carbon dioxide gas. I do want to balance this equation out, and I see two nitrogens, so I'm going to put a 2 here. And then I see, looks like I'm going to have to double this up to make this even 2 here, and that looks like it's all balanced from there. Okay, so let's do oxidation numbers. Again, this is just a glimpse of Unit 9. I know oxygen is -2, so this nitrogen is +2. Oxygen is always -2 unless it's peroxide, but I know this is not peroxide. So this is the nitrogen, or the carbon is +2. Nitrogen here is 0. It's an element, free element, so it's 0. +4 -2. Hopefully you can see the mathematics. Each oxygen is -2 times it by 2 gives you -4, so this carbon must be +4. These are all oxidation numbers, and what oxidation numbers are are basically the electrons that are involved in bonding. So essentially, two electrons that are in nitrogen are involved in bonding with the oxygen here. So two electrons from oxygen is involved in bonding. So this just really tells you how many electrons are involved in bonding. If you draw the Lewis structure for carbon dioxide, you'll notice that all four of its electrons are involved in bonding, two of which are sigma bonds and the other two are pi bonds. So that's why there's a +4 here. Two electrons are involved in bonding for each of the oxygens. So you could play it out with each structure. You'll notice the number of electrons involved in bonding are what we call the oxidation number. So if you look at how the oxidation numbers have changed between the same elements, so between nitrogen here and nitrogen here, the oxidation number has gone down, so it decreased. When you have a reduction of oxidation number, we call that reduce. The substance has been reduced. Who has been reduced? Nitrogen in nitrogen monoxide has been reduced to this nitrogen here. So specifically, the nitrogen has been reduced. Okay. Now, if you see the oxidation number increasing, now where you have a reduction, you always have an oxidation. So notice how the carbon has been oxidized. So that's an oxidation. And what that means is the carbon has lost electrons, whereas the nitrogen has gained those lost electrons. And thus, reduction is a gaining of electrons, and then oxidation is a loss of electrons. So there's an electron exchange between these species in this chemical reaction. And that's what's the driving force. The driving force is these substances no longer have they're not the original self that they were in the reactant side compared to the product side. They have undergone a chemical change. All right, moving on to B. On letter B, you're asked to write the Kp expression. Now I sense that for me to be asked to write the Kp expression, which is the partial pressures of the products raised to their stoichiometric coefficient over the reactants. So I have a balance equation for that reason. So here's my product. My product is N2 raised to its stoichiometric coefficient, C2 or CO2 raised to its stoichiometric coefficient. And then of course my reactants are NO, partial pressure of NO raised to its stoichiometric coefficient, and carbon monoxide to its stoichiometric coefficient. And this is all partial pressures. That's why this is a Kp equilibrium constant. Now let's go to C. In letter C, you're asked to find, you're given information about the heat of formation. It looks like the G formation values of each of these substances. Now you're going, where's nitrogen? I don't see nitrogen. Well, because nitrogen is a pure element, we know that nitrogen's G value is 0. So it's assumed that you all know that nitrogen's G formation value is 0 because it's a pure element. And when you form nitrogen from the original nitrogen, the original pure element, you see no change in Gibbs free energy. So to calculate the G of formation, we're on C, Roman numeral 1. So C1. And this is 1. You're using the G formation, or the G of the reaction is equal to the G of the sum of the G products minus the sum of the G reactants. So G formation products. I like writing the equation down so that I can get used to being familiar with these equations and knowing that they're all on the equation sheet. So please look it up as a way to help you to understand. And again, I know it is this equation because I see formation, F formation. So I'm going to use formation values, or the equation for formation. I do my products. My products would be these two substances, and I do have to stoichiometrically factor that in. So there is 2 carbon dioxide, so I look at carbon dioxide and I have to double this value. 394.36 times 2. And I'm going to bracket this part because I'm done with the products. Again, nitrogen is 0, so that's why I'm not going to factor that in. The reactants, there's 2 reactants to be considered, and you're given G formation values of both reactants, but you also have to double each one, so be very, very vigilant that it's per 1 mole of the substance. Since you have 2 moles of nitrogen monoxide, you're going to take 86.55 and double that. And then you're going to also do that for carbon monoxide and double that and add those together. Now, upon calculating, I do get a value of negative 687.52, but I'm going to cut that off for sig fig purposes. And this is my kilojoules. Now I have to do Roman numeral number 2. Roman numeral number 2 says the heat of formation is given to us, and that is in kilojoule. It's negative 746 kilojoules per mole. Calculate the value for the S. Oh, okay, so we've got G here. This is my G value. I've got my H value right here, and they're all consistently the same unit so far, and now I have to calculate my S. So I'm going to use that comprehensive equation, which is, again, practice writing the full equations so that you can get used to being familiar with what you're doing. So I'm looking at G, the enthalpy, change in enthalpy of the reaction, minus T times change in entropy of the reaction. Okay. I'm going to plug all my values in. My G is negative 687.5, and I'm going to remember that's in kilojoules per mole. My H is in negative 746 kilojoules per mole, so I'm also going to remember that. That means my delta S is going to be in kilojoules as well. So temperature is 298 Kelvin, and then my S is what I'm looking for, the standard change in S, enthalpy. And so when I solve for my delta S of my reaction, I get a value of negative 0.196 kilojoules, and I'm going to leave it in kilojoules per mole. And notice I know the unit to be in Kelvin, because if I were to unit analyze this is in kilojoules per mole, this is Kelvin, and so when I subtract my kilojoules per mole with each other and then divide it by my Kelvin, that's where I get kilojoules per mole divided by Kelvin here. I'm going to erase some of this so I can do my next step, which is D. So I am going to work through letter D. D is given your K constant, your Kp value, and then it says in an urban area, typical pressures of gases are the following. So I don't know if these pressures are actually equilibrium, so I'm going to assume it's not at equilibrium, so I'm going to do what is called a Q calculation. Once again, I'm going to erase everything. You'll see me pause and unpause, and you'll see it all erased. Now, I said you'd see it all erase, but I lied. I rewrote actually the Kp because I really want to make sure I substitute and square what I should square of this reaction, okay, for my Q. So I'm going to calculate my Qp and calculate my QP. I'm going to substitute all my values in. So N is 0.781. And there's no units to my K constant, so I'm not going to put units in there. I'm going to square that, remembering to do that. My nitrogen monoxide is 5.0 times 10 to the negative 7th. Also going to square that. And then my carbon monoxide is 5.0 times 10 to the negative 5th. Square that as well. So all my values are set in order. My Kp, when I calculate it, ends up being 1.20 times 10 to the negative 10 to the 14th. Now, I can actually do some analysis with this Kp. It looks like my Kp is a lot less than my Q. So that means knowing that K is products over reactants, I'm always products over reactants. That means I'm going to need to increase the products to reach equilibrium. And that would mean favoring my reaction is going to shift to the forward direction to try to reach equilibrium where QP equals KP. Okay, so let's go ahead and do the next step, which is to calculate the G. It looks like G, notice how there's no standard conditions, so there's no degree symbol up there, so it looks like it's non-equilibrium G here, which means I'm going to use my equation, and I'm doing part 2 here. Wait, sorry, I'm still on part 1. Yikes. Part 1. And so I would use my equation of delta G non-equilibrium equals delta G equilibrium plus RT ln of Q. So I'm plugging all the variables in. Now, where's my delta G standard? Well, I found that from the previous part, which is right here. I found it to be negative 687.52. So that was determined previously. So negative 687.52, and that's in kilojoules per mole. I'm remembering that so that I can keep my units consistent. Now my R is 8.314, and the units for R is in joules per mole times Kelvin. So I'm going to convert my R into kilojoules. And that will give me kilojoules per mole times Kelvin. And then my temperature is 298, because my Kp value, or that's what it asks me to do. And then my ln of Q, which is 1.20 times 10 to the 14th. So I plug that all in, and I get your delta G equaling negative 607.2 kilojoules. I know it says down here that's 0.5, but I changed it actually on your notes. It's 0.2 kilojoules per mole of the reaction. This is your, and so what does this say? This says that in the forward direction, which is the direction of the reactants becoming products, this reaction is spontaneous. A negative delta G for that forward reaction means the reaction will occur. And it's spontaneous in the forward direction under these specific partial pressure conditions that we have outlined. So that's a full problem. You do want to make sure you're practicing each of these different problems. They will be given sometimes different values, whether it's G formation or they might give you enthalpy. Some problems integrate enthalpy with entropy in it. So you're using the comprehensive equation. There's a lot of ins and outs with these problems. You want to practice as best you can through all of them. You're going to go from FRQ number 1 here, from here on out, to practicing through FRQ number 12. This is actually a very short, this whole unit is quite short. So FRQ 1 through 12, and you'll be given some review kinetics, whether it be going back to kinetics or just, let's see, there's some problems dealing with kinetics, initial rate method, um, there's solution chemistry, equilibrium. So there's a lot of integrations of ideas from the past into this whole unit. It's a very comprehensive unit. So work through the FRQs one by one. Okay, now we get into calorimetry. It's the study of calories, which is energy, heat energy specifically. A calorimeter is used to measure the heat exchange between objects, and usually a calorimeter is it's an insulated object like a double-nested styrofoam, like you see here. And we tend to have a cork that also is a great insulator. But then we have a thermometer sticking inside here, as well as a stir to make sure the heat is evenly distributed and measured inside this double-nested calorimeter. Now, as you have the stir and the thermometer, usually the medium of choice is water. Water has a high specific heat capacity, so we tend to use water as the medium for which in which the reaction takes place or heat is transferred between an object and water. So this is what your setup is usually in a calorimeter. We'll go through all of these terminology. You have seen many of these words already. You haven't seen the word heat capacity per se, but heat capacity is actually what we use for the actual calorimeter itself. So it's the amount of heat to raise the temperature of a given quantity of substance by 1 degree Celsius. This variable is calculated for the calorimeter in a constant value measured experimentally for that particular calorimeter. For the AP exam, the heat capacity for the calorimeter is often negligible and not accounted in heat calculations. In other words, this value, the capital C, heat capacity, is actually 0. So it's negligible and 0 in terms of the in the heat calculations. The specific heat capacity, this is small c, and it's the amount of heat to raise 1 gram of a substance by 1 degree Celsius. Now that's very different from heat capacity, where you're not even given the mass of the quantity of the substance. It's just, but here you're given the mass of the substance, and so that's why it's very specific to the capacity of heat that can be absorbed by that substance or released by that substance. The molar heat capacity is very similar to the specific heat capacity, but instead of 1 gram, it's 1 mole of the substance to raise it by 1 degree Celsius. You want to watch for your units of measurements, obviously, with molar heat capacity versus specific heat capacity. One is grams, the other one is moles. I like the word molar because it does insinuate moles. Heat is measured. Heat is calculated, and it could be absorbed or released. Q is always positive, where delta H could be positive or negative depending on if the heat is released or heat is absorbed. So these are all the equations you're going to see. Here's the calorimeter one, which can be assumed to be 0 in most cases. as long as it's stated that the calorimeter absorbs no heat. So it's oftentimes zero. Um, when you engage in a phase or no phase change, this is the equation to use, Q equals mcat. And then, of course, if there's a phase change of some sort, you're using enthalpy because you're breaking up the intermolecular forces as you go through a phase change. And so that's why you're seeing a different equation to use because, and plus, there's no change in temperature during a phase change. So you can't really calculate Q using this equation. You have to have a different equation for what is happening, changes in potential energy versus kinetic energy as you're going through phase changes. Here are all the variables in terms of what you will expect. Let's go through an actual calculation. Okay, so you have here the mass of metal X at 98 degrees Celsius, and it's lowered into a styrofoam cup a double nested styrofoam cup calorimeter that has a mass of 1,200 grams of water in it at 20 degrees Celsius. The final temperature of the water, because the thermometer can't be, you can't stick a thermometer into the metal. You can stick it in the water and you can measure the temperature of the water. So the final temperature of the water is 34 degrees Celsius. And that final temperature is the same final temperature for the metal as well. What is the specific heat of the metal? Specific heat of water is given to us. Assume the calorimeter does not absorb any heat energy. So here it now kind of relieves us of accounting for the calorimeter's mass. It's actually, its heat absorbance at 0. So that's why I have 0 here. So the heat loss by the metal, so negative Q by the metal, is gained by the water and the calorimeter. But again, the calorimeter is 0. So I set up all my equations as I see. Water doesn't go through a phase change, so it's just Q equals mcat. And as well as the metal doesn't go through a phase change, so it's Q equals mcat. Now the reason why that negative is there is because when you take the difference, the metal actually decreases. Its final temperature is lower than its initial temperature. So that's why the difference of the change in temperature is going to be a negative value. And that negative is nicely opposed by, or the opposite of that sign is going to be imposed upon that negative delta T to make it positive in the end. So calculated, here's the mass of the metal, 120. The specific heat capacity is what we're looking for the metal, and here's the change in temperature of the metal. Now we go to the water side. So the water is 1,200 for the water, mass of the water. Specific heat capacity of the water is given to us. And then the change in temperature. So the water goes up in temperature, so that's why the temperature change is going to be a positive value. Once again, the heat gained by the calorimeter is assumed to be 0. And that's why we use materials like styrofoam to make sure that styrofoam doesn't absorb heat very easily. It actually is a great insulator. So you calculate it all and you get your specific heat capacity of 9.15 joules per gram times degrees Celsius for the metal's specific heat capacity. Alright, now we go to a different problem. In example 13, you're given grams of benzoic. It undergoes combustion in a constant volume calorimeter. And the calorimeter's heat capacity is given to us here. What is the expected change in temperature of the calorimeter? Okay, so the first thing you want to do is calculate your grams to moles of the benzoic acid, and that's what I've done here. We know that the heat, it undergoes a combustion reaction, so I'm going to calculate Q of that reaction. And it tells us exactly how much energy is in that combustion right here. So the enthalpy of combustion is actually negative 3,226.7 kilojoules per mole. So I take that, and I know per 1 mole of the benzoic acid, so I take that moles of the benzoic acid and multiply by the heat of combustion. the change in enthalpy of the combustion. And I get my heat value from here. Now, my heat value, I know that the heat lost by the reaction is going to be gained by the calorimeter, and I know the heat of the calorimeter, or the heat capacity of the calorimeter, is given to me as 853. So I'm trying to find the change in temperature. And then this is the heat of the reaction, which is a negative of its release because it's combustion. And so that's why the negative of a negative is a positive. Again, the change in temperature will be a positive value for that reason. So that's my calculated change in temperature. Now, benzoic acid undergoes combustion in a constant volume calorimeter with, again, the capacity of the calorimeter that contains water in there. So water is going to absorb that heat from the combustion reaction. And what is the expected change in temperature of the calorimeter as a result? Once again, I'm still going to do what I normally do, which is convert my grams of benzoic acid to moles. And I would still calculate the heat produced from that reaction. Once I calculate the heat produced, I put it into this heat flow statement. The heat lost by the reaction is going to be gained by the calorimeter plus the water, because there's water in the calorimeter now. And so I'm going to substitute all my variables in. This is in liters, so that's really 800 milliliters, by the way. And we know that 1 gram equals 1 is per 1 milliliter because the density of water is 1 gram per 1 milliliter. So however many milliliters I have is how many grams there is, and that's 800. And I find out that the heat capacity the specific heat capacity of water is given to us. The change in temperature here is going to be the same as the change in temperature here. The change in temperature of the water is going to be the same as the change in temperature of the inside the calorimeter. And so the change in temperature is discovered or found out to be this. And so why was the change in temperature so different here versus here? It's so significantly more here because all you have is the calorimeter and the air that's in that calorimeter, whereas here you have water to absorb a lot of that heat, and that's why the change in temperature is going to be lower comparatively. All right, so this is a little 3 different types of ways to calculate heat. It's really important to write a heat flow statement. I did forget to mention, and heat flow statement is always where is the heat exchanging, who's losing it and who's gaining it, okay? More often than not, your calorimeter's heat is going to be 0 in most of your AP problems, okay? But if you're given the calorimeter's heat capacity, that means it's not 0. There is a heat, a level of absorbance by the calorimeter itself. But notice my black. In black are my heat flow statements. I'm always going to write that to help me to flow through what equation to use and how to utilize them in the end. Go ahead and do the rest of the FRQs from here on out. Work through FRQ 13 all the way to FRQ 16, and that will end pretty much this whole unit, just working through some FRQs, the AP set problems, as well as all the MCQs for this unit. So this ends Unit 6, onto Thermodynamics. It's pretty straightforward as far as the whole unit's concerned. Knowing when to use which equation is very important. Knowing some of the concepts, still understanding equilibrium so you can translate it into interpreting whether a reaction will be thermodynamically favorable or not. And then just make sure you work through the AP set problems and the rest of the MCQs. And then work through the rest of the AP questions and this AP set problems. This is quite a short unit, and I think it's quite straightforward. You're not going to see any tricks of the trade. Just make sure you're practicing through all these FRQs and the AP set problems.